Modern physics starts with a branch that we call atomic. Now, when we talk about atomic physics is just where we talk about how we came about the nature of an atom. So before we even say anything on that modern physics, we have to first talk about atomic. And atomic physics is equal to atomic structure in chemistry. They are like the same thing. And they are very sound in atomic structure in chemistry. You do plenty things on the atomic. And what are these things telling us? What do we do as an atom? What an atom? Atom is what? Of an element. I don't know. They said atom is the smallest indivisible particle of an element. And one man that we call Dalton. I don't know. He gave us 5 assumptions of an atom. Yes or no? Yes. So what are the 5 assumptions? Number 1 is definition. I don't know. Yes. Number 1 is atom is the smallest indivisible particle of an element. What is the second one? That conservation of atom. Yes or no? Yes. So what's the third one like that? Okay, atom of the same elements, they are like not as well. But differs from atoms of other elements. Yes or no? Yes. So what is the first one like that? That is not combine atom, they do so in simple numeration. Yes or no? Yes. So what is that one? Now, for chemical combination to occur, there must be combination or subtraction or the separation of what? Of atoms. Now, look at it. Those 5 assumptions, at the end of the day, we start saying Dalton is lying. That is, we have something for multiplication of that symbol. Yes or no? Yes. So they modified 4 out of 5. Yes. So the first one they modified was actually yes or no? Yes. That is, we have something called some atomic percentage. And one of the subatomic percentages that we have is neutron. Electron is positively charged. Yes or no? Electron is negatively charged. And for the neutron is neutral. Now, there's not something when we are from that aspect, I'll go to one place that we call atomic model. That is the first model that we have was the model by J.J. Thomson. Now, J.J. Thomson was telling us something. Look at it. This atom that you are studying, this atom that you can see, naturally, it's not that you can see atom anywhere. And it's not that you can just go to one lab and you tell them, inside this lab, we are doing that. And all you see to one chemistry lab and you say, we have very atom research. You cannot see any atom. It's light. So the best thing you can do is that this atom, people start giving us model. Model means they start thinking about how the atom look like. And they start thinking about what can be inside the atom. It's just like as you just sit down somewhere and you say, okay, I want to know a model of how God look like. You know, if you start to know a model of how God look like, you did not see God. Have you seen God? No. Okay, you did not see God, but you want to know how he look like. So you are now reading things and you are now giving suggestions. And you are doing experiments so that it's possible this thing look like this. So J.J. Thomson actually gave us a model of an atom. Now, inside J.J. Thomson's model of an atom, we have embedded electron. Now, we have embedded negative particles. They are not called electrons. We have them embedded negative particles. We have them inside positive particles. That is, they show a lot of positive particles. They now show that they are negative particles inside. So J.J. Thomson gave us that model of atom. Another person that came at the end of the day and said, J.J. Thomson, you are 9. Because that one said doing an experiment. They call that one Sir Ernest Rutherford. They call him what? Sir Ernest Rutherford. Now, Sir Ernest Rutherford gave us another model of an atom. And he called it the planetary model of an atom. Now, have you seen undergraduate? Have you seen anywhere the planet move around the sun? Yes. They don't move, they revolve around the sun. Yes. Have you know? Yes. That is, you have planets. Now, he actually said that the sun itself is actually one center that all electrons now move around it. But he was talking about planetary. But one of his students, at the end of the day, now modified that planetary model of an atom. And the name of that student is Neogua. The name of that student is what? Neogua. So this student, Neogua, was the first person to give us the model of an element. And the element never gave us the model of his hybrid. The element never gave us the model of his what? Hydrogen. Now, he gave us hydrogen model. That is, we know how hydrogen looks like. So at the end of the day, when we start drawing orbitals, that we say there is one center in an atom. That is the center of an atom is called the what's the nucleus. The center of an atom is called what? Nucleus. And inside that nucleus, we have two things. The two things that we have inside that nucleus is what? Electron. We have proton and neutron. It's proton and neutron that we have inside a nucleus. We're gonna go with nucleus, neutron. So neutron is inside and proton is inside. And everything that is inside the nucleus is the one that actually gave us mass number. It's the one that gave us what? Mass number. So they ask what is the mass number of an element. The mass number of an element is number of neutron plus number of neutron plus number of what? Now, when we now have that nucleus at the center, the thing that is now moving around the nucleus is now something we call electron. It's something we call electron. Now look at it. We used to say it normally that like charge, they repel and unlike charge. Yes or no? Yes. Now, you say the center of an atom, we have nucleus. Yes or no? Yes. And that nucleus now, you say it is proton and neutron. That is, it is positively charged. Yes. It is positively charged. Yes or no? Yes. You can't say one person they move around it, and that person that is moving around it is negatively charged. That's electron. Yes. Now, if electron is moving around it, look at it. Let's assume I used to attract short people. Now, if I used to attract short people, someone that is short, that is very close to me, and someone that is short, that is very far to me, which one will easily, come close to me? Yes or no? Yes. Now, not far away, that one that is far away, the person has energy than the person that is close to me? No. Yes. Yes. Okay. The person far away, who has energy most? How is the person far away and the person close? It's the person far away that have high energy. Because it's when the person that is far away, when his energy drops, that's when he will come close. You don't know, I'm using a force to pull him now. I'm using a force to pull him. The reason why he's far away is because he has a lot of energy. The reason why he's far away is because he has a lot of energy. He's resisting it. Yes or no? Yes. And so when he loses energy, he will now come close. When he loses energy, he will not do what? He will not come close. He will not come close. So at the end of the day, in physics, normally in chemistry, you draw something, you draw your orbitals. Yes or no? Yes. You have K, L, M, N. Have you know? Yes. And you have something called azimuthal number, azimuthal quantum number, yes, magnetic quantum number, spin quantum. Have you know? Yes. We have period, we have groups, we have table, we have electropositive elements. Yes or no? Yes. Positive is group 1 to 3. Yes. I don't know. Yes. Group 4 is group 1 to 6. Yes. Yes. Example carbon. Shaping out. And group 5 to 8. No, group 5 to 7. Group 5 to 7 are electronegative. Why group 8 are what? No class. I don't know. Yes. Now, when we know all these things, those ones they are in chemistry, they are not in physics. But we have to have idea of what these things under atomic. Because that's not going to access. Now, the man that discovered electron, I said this point in this class. Who is the man that discovered electron? J.J. Thomson. I don't know. Yes. And the man that discovered proton is what? It's that one that discovered proton. And the man that discovered neutron is what? The man that discovered is James Chadwick. James Chadwick. Now look at it. One man created an experiment. One man made one experiment that we call the oil drop experiment. And his name is R. Eminent. His name is what? R. Eminent. Now, R. Eminent gave us the oil drop experiment. Now, this oil drop experiment, we used to know plenty things. We need to know charge per unit mass of an electron. We used to know what? Mass of an electron. Now, charge of an electron. We have what I call that is there's something called drop of energy. That is energy can drop from one state to another. Now, when we are not talking about all these things, the time we now start to talk about atoms and elements, we now look at one of these properties and one of these natural things that we used to see. And there's something that creates the universe. The universe is very complex. And it's under modern physics we actually talk about the universe. Look at it, there's one year like that, I think 1924. Yeah. I can't know it's 1 year. There's one like that, there's no conference they used to do on that physics. Or in science, it's not that physics, in science. There's one called, let's call it Solving Conference. Have you heard of it before? No. There's no conference, let's call it Solving Conference. I think they did one in 1927, but they are meant to do it in 1924. Now, that Solving Conference is through that Solving Conference, they changed the topic. Normally, this modern physics we are doing is not actually called modern physics. We started with classical physics. We started with what? Classical physics. And classical physics is talking about those two things. It's talking about the position and momentum of an object. It's talking about what? The position and the momentum of an object. Anything we are interested in is just the position. So once you know the position where objects stand in the universe. So at the end of the day, they now change that classical physics to modern physics. And when they want to change it from classical physics to modern physics, they have the survey conference. And in that survey conference, we have about testing in attendance. We have, I think we have Madam Fu. We have a lot of scientists in attendance. Now look at it. When we now talk about quantization of energy, that energy can drop from one place to another. Yes or no?
Yes.
Yes or no? Yes. Now we now look at something that controls the universe. And one of the things that controls the universe is what we call light. Is what we call what?
Light.
Now look at it. When we are talking about light, immediately you hear light, the thing that will come to your head is wave. Immediately you hear light, the thing that will come to your head is what? Wave. Because you believe that light is a wave, it's an electromagnetic wave. Because under electromagnetic wave, we say we have 7 electromagnetic spectrum. Yes or no? Yes. And one of it is light. And light is the one that is moving with the velocity that is 3 times 10 to the power 8. Yes or no? Yes. That 3 times 10 to the power 8 is light. So we believe light is a wave. But they now tell us otherwise, that this light is not only a wave. Light also have particles. Light also have what? Particles. That this light can now behave as wave and particle. Light can now behave as what? This thing is now very easy. When they now say light has particles, immediately they say light has particles, they now say okay, light can behave as photons. Immediately light can behave as photons. So what can light now do as this particle? Light as particle is now what we call photons. It's now what we call what? Photons. Photons. It's now what we call photons. It's now what we call photons. Now, light as particle now, we now say we have effects that this light as particle can do. That's that since it can do. Number one, it can eject electrons from a metal surface. It can eject electrons from a what?
Metal surface.
And that's what we now call photoelectric effect. That's what we call what?
Photoelectric effect.
That is, at this point, we want to use light to eject electrons from a metal surface. But naturally, before that time, they told us something about energy. That is energy of this light. That is, there's someone who called Sahaba testing. Those years when they want to fight the Second World War, Sahaba testing was the one that gave us. Who have watched this movie? Open me. Okay, influence of what you read. Which movie like do you know that's the best movie to come out of 2020? I'm sure that's the best movie to come out of 2020. Go and watch Wicked Blinders. After that, we want to. Okay, it's only book used to read. If you really want to find modern pieces being interesting, go and watch it. Look at it. In that movie, Oppenheimer was a scientist and he was called father of atomic bomb. In that movie, they actually showed how they created the atomic bomb that they used to do Hiroshima in Japan. Thank you. Do you know it's Hiroshima they blew in Japan? So you don't want to read it. It's not much now. And that's the best thing to come out of. Now in that film, they actually showed about testing. About testing was inside that film. This embark was there. What is it? It's not that they mentioned that people acted them. People acted them. And the person that asked Eston looks like Eston. They gave him the costume of Eston. People acted all of them. So all of them look alike. And you be like, you understand them things. They actually even showed their lectures. Never was inside the film. All this rubbish I'm telling you is inside the film. I'm serious. I don't know if you watch from Balani Bonlepo in the world. Don't date. You don't know all those kind of things. They are teaching you how to steal. That's why you know how to steal. But if you want good thing, you want to create atomic bomb. What's the name of this? Sambisa. Sambisa boy. But for you. Now look at it. Before that time, Abatestin gave a formula. Is that formula they actually use? Because Opemia is actually a theoretical scientist. Is a what? Theoretical scientist. Now, this modern physics is like the best part of physics. Do you know why it's the best part of physics? It's story. And students like story. All of you like this, you love story.
Yes.
Have you not like story?
We love story.
But don't worry, it's that story that will come at me. Yes. But look at it. This Opemia is a theoretical physicist. What we mean by theoretical physics is that it knows only theory. It cannot do 2 plus 2. He might miss it. He don't know any calculation. And this person, if he's inside the lab like this, boom, come on, follow already. Tó bá ṣe di restore by restore ti fọ́. Tó bá ṣe di kí n bá gbogbo ẹ̀ ṣáà máa ń bàjẹ́, like since the evaluation for in his hand. But he can write stuff and tell you that if you do this and do this and do this, this will happen. So it's someone that knows what will happen, but it's not someone that can actually do that thing that will happen. So Opemia actually needed people. He actually needed a physicist that is going to help him with his calculations. But in the past, Abatestin has shown one calculation about energy. And Abatestin has talked about energy of light. Now, when Abatestin talked about energy of light, Opemia now going to meet Abatestin again when they want to create the atomic bomb. So now going to meet him that we want to use your equation for this bomb and stuff like that. But Abatestin rejected. And the reason why Abatestin rejected is that Abatestin wants peace among the world. Abatestin is a very good man. Like he wants, even though he used to do stupid things, but he wants peace. He don't want war. Because he knows that anything that happened that time, anything the bomb is going to do, is going to turn to a weapon. It's going to turn to a what? A weapon. That is, they will later use science as a weapon. So at the end of the day, they actually turned into a weapon. And Opemia actually went to a deal or something. They tried to deal with him before he died. So look at everybody. When Abatestin talked about that energy, you now say energy, or this energy that we are talking about, is now the one we call HF. They got this H from Planck's. Yes or no?
Yes.
And they call this H one name. It's already inside your note now.
Yes.
They call this H one name. They call it Planck's. They call it what?
Planck's constant.
It's a constant. That's the value.
Yes.
What is the value?
6.634.
I used to tell students that don't put constants in your head. Do you know?
Yes.
Don't put constants in your head, I'm sure. Nobody will ask you what is Planck's constant in JAM. They will surely give you. If they ask you a question, they will put brackets. Planck's constant is. Share here.
Yes.
So at the end of the day, they call it Planck's constant. So we say E is equal to HF. We now say this F itself is frequency. But we say velocity is equal to F lambda from wave. Because this light itself is also a wave. Yes or no?
Yes.
So at the end of the day, this V that is here is the velocity of light. And velocity of light is now C. So C is equal to F lambda. Very good by lambda. Lambda will cancel lambda. So F is equal to C over lambda. So when we say F is equal to C over lambda, can I bring this back here?
Yes.
So I'll just say E is equal to AC over lambda. Do you get what I'm saying?
Yes.
Now we now talk about photoelectric emission. That is what we now say is that a metal surface now. I now want to use light to eject metal, like to eject electron from a metal surface. If I now want to use light to eject electron from a metal surface, look at it. It's 2 things I'm going to do. Number 1, I'm going to have a metal surface. Look at this metal. I have A here, I have B. This metal A B. And I carry light, a source of light. That is, I have a source of light here. This source of light, and I point it here. Immediately I point this light here. Remember, which energy am I going to use to point this light here? E is equal to HF. Yes or no? Yes. That is energy that this light is going to use. E is equal to HF. Immediately this light reaches this place. This light wants to do 2 things. Number 1, it wants to carry electron. That is, it wants to eject electron. Number 2, it wants to carry uranium. Number 2, it wants to do what? Carry uranium. It's just like a tip that wants to stay transformer. Just imagine that a tip wants to stay transformer. If you want to steal that transformer, you have seen a transformer for that big transformer. Yes. Now, I think I heard it somewhere, I don't know. Maybe all this copper latte or something. I shall know. Okay, who had copper latte yesterday night? Are you doing so? Yeah, you do. Yeah. You are just reading. Yeah. I love you. Me, I hate copper latte. Yeah, copper latte. I love all those stories. It's very sweet. Now, look at it. Look at it. If someone wants to see transformer, so we have a transformer game. It's 2 things you are going to do. Number 1, you first think of how you carry transformer inside your car. Above this way you the first think of how you carry transformer inside your car. Number one, yes or no?
Yes.
That is you use one energy to carry it inside your car. Number two, you now think of how you carry the transformer and do it. Yes or no?
Yeah.
So it's two things you want to do. Immediately this light touch this metal surface. It's two things you want to do. Number one, we will call big electron. We actually take the transformer. Number two, we have big electron and we have big jackpot. Now the energy to now use to carry the electron, to eject the electron from this metal surface is now the one we call work function. It's now the one we call what?
Work function.
The energy is going to use to work. That is the energy is going to use to eject electron from the metal surface. Is what we call what?
Work function.
To what my big jackpot is now kinetic energy. It over big jackpot is now what?
Kinetic energy.
So look at it, two things now. I would now say this energy that this light now use total is now equals to work function it will be ejected plus what?
Kinetic energy.
The energy will now becomes work function plus what?
Kinetic energy.
But what is energy? You say energy is HF. Yes or no?
Yes.
So I will have HF to be equals to work function 2 is a form of energy. Work function 2 is a form of what?
Energy.
Remember I called work function and energy. I said it's the energy you use to eject electrons from a metal surface. Yes or no?
Yes.
That is work function itself is a form of energy. So work function itself too is HF. But this F which is F last one is now F naught. And this F naught is called what? It's called Freyud sequence. It's called what? So scheduled frequency plus kinetic energy. So at the end of the day, can I make kinetic energy of the formula? Can I make kinetic energy?
Yes.
Yes, what would I would have kinetic energy. So because HF minus HF. Yes or no?
Yes.
So kinetic energy now goes to H into bracket F minus F. This kinetic energy. Remember, energy is equals to work function plus what?
Kinetic energy.
Energy is equals to work function plus what?
Kinetic energy.
So at the end of the day, our kinetic energy equals to H into bracket F minus F. This F is the normal frequency, yes or no?
Yes.
And what is F naught? It's called what?
Threshold frequency.
It's called what?
Threshold frequency.
This everything about photoelectric emission. This everything about what?
Photoelectric emission.
Go through your series questions for photoelectric. 20 questions. 20 questions. You have this assignment.
No.
Let's see one or two questions before I emphasize that.
Any cup?
Cocky.
Your darling.
If the actually mix a material, if they mix with a material, the material will decay. Or they are going to do something that will call disintegrate. They are going to do something that will call
Disintegrate.
That is, they are going to disintegrate when they are with a material. Look at it, naturally, we have three particles that we talk about. We have alpha particle, beta particle, we have alpha particle, beta particle, gamma rays. Mass number, look at it, mass number is proton plus neutron. Look at it, you should work on your atomic structure like mad. Mass number is proton plus neutron. Neutron itself, no man change, proton will never change. Yeah. Proton will never do what? Change. Proton will never change. You only add or gain, you only lose or gain proton. You cannot lose or gain proton. It's only neutron you can lose or gain. It's only neutron you can do what? You can lose or gain. So you cannot lose or gain this guy. Because you cannot lose or gain proton. That is your mass number that is different. Is due to neutron number. So when they say atom have the same atomic number, atomic number is number of proton. Atomic number is number of what? Proton. That is, if they have the same atomic number, that is, they have the same proton. They have the same what? Proton. Now, Kiwala mean by we have the same electron. We have the same electron means maybe we are both neutral. Maybe we are both what? Neutral. I was telling you guys earlier that when we have sodium, when we have someone like sodium, sodium have 11 proton and 11 electrons. Yes or no? Yes. But at the end of the day, we have sodium ion that I call Na plus. Yes or no? Yes. This Na plus now have how many protons? 11. But how many electrons? 10. Torí ó ti lọ ṣe quadruple, ó ti actually ṣe octet rule. Because normally sodium is 2,8,1. Yes or no? Yes. In the outer shell, in the valency is meant to have what? 8 electrons. Yes or no? Yes. Ó wá mú ẹyọ kan tó ní ìmú yẹn ó wá fún yàn. It can't give person like chlorine. In that bó ṣe fún yàn báyìí, òun ti lose electron kan. So at the end of the day, this proton, like this sodium, like it has lost 1 electron. Yes or no? Yes. So this sodium and this sodium ion and normal sodium, they have the same proton. They have the same number of what? Proton, which is 11. But they have different electrons. Yes. Are they now? Yes. Now, we need not say this guy and this guy, they are isotopes. Are they isotopes? Are they isotopes? No, they are not isotopes. Because at the end of the day, the mass number of this guy is 11. Yes. The mass number is 23 and the atomic number is 11. Yes or no? Yes. For this one too, the mass number is 23, the atomic number is 11. Because proton did not change and neutron did not change. Proton did not change and God did not change. Yeah. So in that question, what they do? Isotopes have equal number of electrons and protons. They have equal number of what? Electron and proton. Option C. The same atomic number but different number of neutrons. Now, they have the same atomic number, yes or no? Yes. But they have different number of neutrons. Yes or no? Yes. Down to zero. Next one. The same number of other particles, that's one. They don't have the same number of other particles. Yes or no? Torí ìyẹn ti lose particle. Particle wo nìyẹn? Neutron. They have different number of neutrons. Yes or no? Yes. Please understand the concept of proton, electron, and neutron. Understand the concept of what? Proton, electron, and neutron. You must understand that concept very well. Anytime you see atom, you must be able to say, okay, this number of protons we have. This number of, if you know all these things, if you know all these small things, you know plenty things in science. You already know combination. You know how they will bond together. Know that it's this one that have minus and this one that have positive. They are the one that will come together and bond. Yes or no? Yes. That will now call ionic bond. Yes or no? Yes. You say, okay, this one and this one, they want to share. You now say covalent, you now say dative. Have you now? Yes. You now say dative and coordinate covalent bond. Have you now? Yes. That's how you have all these things. You have to know all these things very, very well. Look at number 31, 1989, question 46. Okay? So, like, I want to be able to leave this last and you can solve all these 129 questions. Because they are very easy. And we've talked about almost everything. Okay? 1989 question 46. They say a radioactive substance has half-life of 2 years. Now, they say if the initial mass is 40 grams, which of the following correctly gives the mass of the substance length at the time started? Now, they say the initial what? The half-life is 2 years. Yes or no? Yes. Now they give us half-life to be 2 years. What do they call the initial mass? 40 grams. 40 grams. Now they not draw one. Is that a they not used to draw from? How How do you know it's open? Now look at it. When the initial mass is 40 years, after 2 years, mélòó la kù? Mélòó la kù after 2 years? You know I told you half life means the time you use to reach half. Yes or no? Yes. So the initial is 40 grams. How many will you remain after 2 years? 20. Yes or no? Yes. So after 2 years, it is 20 grams. If you look at the table in your hand, you see that option C is very big again. So the option C, they write 2 years to be 30 grams. 2 years cannot be 30 grams. Yes or no? Yes. 2 years is what? 20 grams. Mélòó ló máa kù 2 years? 20 grams. So you make 20 grams in 2 years. Now in 4 years, how many will remain in 4 years? 10. How many will remain in 4 years? 10 grams ló máa kù in 4 years. Ṣé nǹkan náà sọ yé yín ni? Ṣé nǹkan náà sọ yé yín ni? Oye, let me explain you. Look at it. Now me explain when I was explaining half-life. I told you that half-life means the time it takes for it to reach half. Half time is the time it takes for it to reach what? Half. For it to reach half, in the time to maintain. Did I say, okay, this half-life of this substance is 2 years. The half-life of this substance is what? 2 years. Initial mass is 40 grams. In 2 years, mélòó ló máa kù? 20. Abi? Yes. In another 2 years, mélòó ló máa kù? 10. Abi? Yes. In another 2 years, mélòó ló máa kù? 5. So in 4 years, mélòó ló kù? 10 grams. In 6 years, mélòó ló kù? 5. That's what they're asking. They now say 2 years, 20 grams. Abi? Yes. In 3 years, they did not give us information about 3 years because 3 years could take half-life. Yes. So it's still 20 grams. Shebi now? Yes. In 4 years, it's now 10 grams. Shebi? Yes. In 5 years, what will be it in 5 years? It will still be 10 grams. Yes or no? Yes. In 6 years, now to share another half-life after 5 grams. Yes. Yes or no? Yes. So which of the options will make sense? A. Eh? A. Okay, option A, yes. It's A that makes sense. Option A makes sense. D does not make sense. So D in 5 years is 0 grams. Chance is 0 in 5 years. No, it is 0. So it's only A that makes sense. Only A that makes sense. In 6 years, it will not be 5 grams. So book is very easy, Jerry. Look at 1989 question 49. 1989 question 49. That's question 34 inside your sandwich. 8 alpha decays. They say 8 alpha decays and 6 beta decays. That's 8 alpha means 8 ions. Yes or no? Yes. They say 8 alpha decay and 6 beta decay necessary before an atom of. They now give us an atom. They say uranium. Okay, you? Uranium have atomic number of what? 90 what? 92. Okay. And that one is 238. Yes or no? Yes. Okay. Can I say? I want to read the question. Yes. 8 alpha decay. 8 alpha decay.
And 6 beta decay.
And 6 beta decay.
Necessary before an atom of.
Necessary before an atom of.
Uranium U.
Uranium U. Continue.
Okay. Achieve stability.
Achieve stability.
The final product in the chain has an atomic number of.
Now, the final product in the chain has an atomic number of. Final product have an atomic number of. When you say decay, that is alpha 8. Don't Jerry can. Alpha 8 don't shake him. That is this 92. I want to remove 8 alpha. I want to remove what? 8 alpha. What's the atomic number of alpha? What's alpha? Alpha is helium. Abi? Yes. That's 4. So 8 helium move helium. 8 helium times 8. Yes or no? Yes. So I have the 8 times 2 is what? 16. So I have 92 minus 16. What's 92 minus 16? 76. Yes or no? Yes. Now Sabi. But it says 6 beta particle. No, no. And beta is like this. Beta is 0 minus 1. Yes or no? Yes. That's 8 times 6. So 6 times minus 1 is what? Minus 6. But look at it. Go to Jerry. That is 76 minus 76 minus what? Minus 6. So minus is that you're new. Minus is that shaking. That you're new. Let's decay down. So that would be minus 6 plus 6. What minus 6 plus 6? So
C for correct.
Like, book is very easy. Do you see what we are doing? Yes. Do you see what we are doing? Look at 993 question 49. That's 51. That's 51. I'll do this 51. You could do 53. This is very easy. Like,
You know all these things, this part that we are just doing now. Why we never miss it? And if Jam will ask you, it's sure. Like Jam will just put it there. Just say, yeah, you want to be sharing. At the end of the day, you should not miss this kind of question. They should not hear it outside. They should not hear it outside. Like, go and miss something like this. It's not nice. We are there, 51 direct.
51.
Okay.
An element.
An element X.
An element X.
An element X.
An element
An
X.
element X.
Of atomic number
Now, they say
88.
element X have atomic number of 88. Yes or no?
Yes.
Okay, continue.
And mass number 226.
Mass number 226.
Decays
Decays
to form an element Z
to form an element Z
by emitting two beta particles and an alpha particle
and an alpha particle
and an alpha particle
and
Z
an alpha particle Z
is represented by
now look at it, they say two beta particle and an alpha particle ni emit. Two beta particle and an alpha particle actually mean emit. Now this thing is very easy. That is, they emit two beta particle, alpha particle, and Z. Two beta particle, alpha particle, and Z. Now, if you look at this thing very well, you see something. You see that we have Z. That is this thing like this. We don't know if is Z. And what you want to ask us is what is the atomic number and atomic and mass number of Z? What is the atomic number and mass number of Z? Did they call this one 88 for us? Yes or no? Yes. Now look at it. One O emit. That is before you O emit Z plus alpha particle alpha and two beta particle beta means. Abi? What's alpha particle? What's the mass number and atomic number of alpha? 4. Yes or no? For beta, what are we going to have? 0 and minus 1. Yes or no? Z now. Remember I told you that left was equals to right. Yes or no? So what would I have there? I would have 226 is equals to, let me call this one X, let me call this one Y. So I'll say X plus 4 plus 0. 2 times 0 is 0. Yes or no? So at the end of the day, I would have 226 is equals to 4 plus X. Therefore, what this will X will be equals to 226 minus 4. What's 226 minus 4? 2. That's what will be here. For YQ Alamani, 88 is equals to Y plus 2 into bracket minus 1. Do you know why it's 2 into bracket minus 1?
Yes.
I have two beta particles. Yes or no?
Yes.
So because I have two beta particles, between the bracket minus 1, happy?
Yes.
So at the end of the day, I would have 88 to be equals to Y plus 2 minus 2. What's 2 minus 2? 0. What's 2 minus 2? 0. So at the end of the day, Y is equals to 88. So what will be Z like that? Z will be equals to kini X, 2, kini Y.
88.
That's the answer. Everybody So that question 53, everybody will not do it now. You not do it yourself. Only because you're running, then you want to say, we are poor.
a certain radioisotope of symbol U
of uranium.
mass number 235
Mass number 235.
atomic number 92
I said number 92. I'll check inside the please.
emits 4 alpha particles
Emits 4 alpha particles.
and 3 beta particles.
Oh, it emits 4 alpha and 3 beta. 4 alpha and 3 beta.
The mass number and the atomic number
The mass number and the atomic number
of the resulting element respectively
is
are
now they are looking for the mass number and the atomic number of the element. Abi now they say it emits when it decay or when it disintegrate or it emits. They are telling that ele go fun wa ni one element that we don't know. Let's call that element X. Ẹja fún atomic mass ní ẹja feeling b plus ó wá fún wa ní 4 alpha abi ó tún wá fún wa ní 3 beta. So we are find this one. What I buy? The two people are true boys and girls.
1987.
1987. Say everybody don't get that.
yes.
Eh. So that's so easy. That's what I do for you. It's very easy like that. It's a party. That's
I don't know. Why you did that? Because I don't want to disturb them. I don't want to disturb them. I don't want to disturb them. Bye-bye. Eh? You didn't want to disturb them. Bye-bye. But don't fool them. Oh, friend. You shall find them too. I'm not even going to be about them.
Do we all get the same answer?
Yes.
Do we all get the same answer?
Yes.
Let's relax, Panama.
Sir?
Let's relax, Panama. Sure, they'll go with it. No going to tell it. I don't want to tell it.
Okay, look at this one. Look at sodium. Everybody look at sodium. Sodium is 1123. Yes or no?
Yes.
Did I say we add sodium to proton?
Quem não sonha, o dama ou a
That's sodium to proton. When we add sodium to proton, we now have X of P and Q plus what are you calling it? Plus alpha particle. Please, can someone tell me what is P and Q? Can someone tell me what is P and Q? P and Q. Proton. We have proton. We add proton to this. What is P and Q? How people take calculation in chat? Sodium plus proton give X plus alpha. Alpha is helium now. So what's P and Q?
They said to show English go. I said some of question mark.
19 hours.
Only you as more you material. It's a good exam. I'm going to the column.
P is 19, Q is 19.
I don't think you can do best of my
P is 20.
I just saw
P is 20, Q is what? 10. Wrong person. P is 20, Q is 10. Look at everybody. Look at everybody. Just saw. Sodium. Sodium is 11 and 23. Yes or no?
Yes.
Plus proton. Kini proton. Proton is 1.
Yes.
Why is proton 1? I say atomic number is number of proton. Yes or no?
Yes.
Mass number is what? Proton plus neutron. Proton plus what? Neutron. Add proton and neutron. So that's 1. So now give X, which have P and Q, plus alpha is what? Helium. That's 4. Yes or no?
Yes.
When you go to the left, you go to the right. Abi?
Yes.
So I say 20 plus 1 is equal to P plus 4. 20 plus 1 is what? 24. 24 is equal to P plus 4. So P will be equal to 24, which is 20. From here, I'm going to have 11 plus 1 is equal to 2 plus Q. Yes or no?
Yes.
What's 11 plus 1? 12 is equal to 2 plus 3. So Q will be equal to 12 minus 2. So Q is equal to 10. So it's 20.
Option C.
Don't use correct. Now look at it. When we're talking about photoelectric emission, I say that I do something here that I say light will carry electron. Yes or no?
Yes.
And I say it's called the particle of light is called photon. Yes or no?
Yes.
And I told you that energy required is equals to work function plus kinetic energy.
Yes.
Yes or no?
Yes.
Now that kinetic energy we used to call it one name. There is one other name we used to call that kinetic energy. The other name we used to call that kinetic energy is called stopping potential. It's called what?
Stopping potential.
Remember I told you that kinetic energy is equals to energy minus work function. Do you remember?
Yes.
And this energy is equals to hf minus hf naught. Why did I call it f naught? Why did I call f naught? Why did I call f naught? So I say it's h into bracket f minus f naught. So anytime you sit inside f naught that they say what is the stopping potential? Stopping potential is also the energy required to carry an electron away from a metal surface. That is, stopping potential is still the kinetic energy. Because when I draw it for you, I say first one thing. The first thing is that we eject the electrons. Yes or no?
Yes.
Now when we eject it, the energy that we use to eject it is one called work function. It's one called Gejapa. It's one we call kinetic energy. I know. It's not the one we also call stopping potential. It's the one we also call what?
Stopping potential.
What was stopping potential? And I believe that before I enter this class, I already told you guys about energy. That energy is equal to HF. Abi now? Yes. And energy is equal to mass. Abi?
Yes.
It's not changing, no. This thing is not changing mass. It's called mass defect. It's called what? Mass defect. So if they ask you, this is mass defect. Mass defect C square. Let's see is what? Speed of light. Abi now? What speed of light? 3 times 10 meter per second. Yes or no? Yes. So energy is mass defect C square. If they ask you a question on this, you should be able to get it straight. And this guy is HF. Yes or no? Yes. As this guy is HF and this guy is MC square, you know I can equate something. I can say HF is equal to mass defect C square. Can I do this? Yes. Can I do something like this? Yes. And I can do something like this. But this F, I said V is equal to F lambda. Yes. But this, I can say divide side by lambda. Yes. If I divide side by lambda, I'll say F is equal to V over lambda. But V is velocity, and we are talking about light. So I can say C over lambda. I can still call this thing HC over lambda. Yes or no? Yes. So HC over lambda can also be equal to mass defect C square. Yes or no? Yes. Yes or no? Yes. Now in physics, we just want to relate things. We don't want to even put formulas in our head. We want to say A plus B is C. We now want to say A is 1, B is 2, C is 3. 1 plus 2 is 3. Do you get what I'm saying? Yes. Now if I say A is 1, B is 2, C is 3, and I say A plus B is equal to C. That is, I'm still saying 1 plus 2 is equal to 3. Yes or no? Yes. That is, immediately you see something in this formula, and you see that in this formula, thought they relate to one and they possible. I say yes. Yes. So one other thing that I've not talked about inside atomic modern physics, and the other thing I've not talked about inside this modern physics is what we call Heisenberg uncertainty principle. It's what we call what? Heisenberg uncertainty principle. You can see it anywhere. Why jam? It's rare for jam to act sharp because jam is not definition and definition kind of. But what Heisenberg is telling us that you cannot get the position and the momentum of an object at the same time. You cannot get the what? The position and the momentum of an object at the same time. Remember I told you that before we started modern physics, we used to call it classical physics. Yes. Yes or no? Yes. Remember I told you we used to call it classical physics? Yes. Now when I told you we used to call it classical physics, I said in classical physics, the only thing we are concerned is about the momentum and the position. The only thing we are concerned is about the what? Momentum and position. So Heisenberg itself is a classical physicist. Heisenberg is a what? Classical physicist. So it's not that tells us that okay, this position and momentum of an object, you cannot find it at the same time. You cannot find it at the same time. That is, it is impossible to get or to discover the momentum and the position of an object at the same time. It is impossible to find or to get the momentum of an object at what? At the same time. It is impossible to get the momentum of an object at the same what? At the same time. At the same time. That's what Heisenberg is telling us. Now let's have a recap of things we've talked about in this class. Let's have a recap. I was talking about atomic physics. I said someone discovered proton. Who discovered proton? Who discovered proton? Who discovered electron? Okay, who discovered proton? Who discovered proton? Okay, I think I want to say neutron next time. Okay, who discovered neutron? James Tadic. And I was talking about neutron, I was talking about models of atom. I talked about 3D models inside this class. I said we have the Thomson model. Yes or no? Yes. I said that time we have embedded electrons inside plenty positive atom. Yes or no? Yes. I say another one. I said we have Rutherford model. I said it's also called planetary model. I said that planetary model is talking about a planet. That is, we have electron moving around something at the center. Yes or no? Yes. That is, they revolve like the planet. And I say someone give us the model of an hydrogen. Who is that person? Nebula. Who is that person? Nebula. I say it's Nebula that give us the model of an hydrogen. And Nebula is a student. He's a student to Rutherford. Now, at the end of the day, we're not talking about atomic physics. We're not talking about atoms, small. And I say we have doubting assumptions. What are the assumptions? Number one. Number one assumption of that says that atom is the what? Smallest indivisible particle of an element. What is the modification to that assumption? Discovery of subatomic particle. Have you now? Like neutron, proton, and electron. Have you now? Another assumption now. Another assumption. Another be what? The multiplication for that one. Total of radioactivity. Yes. Okay, another assumption. What did I call the multiplication? Abina. What did I say isotopy? Say what? Yes or no? Remember I told you it's due to their different what? Don't forget that due to their different neutral number. Now, what's the fourth assumption?
When a number they lose all the simple whole number ratio.
Now, let's look at the multiplication of that one. The multiplication of that one is in organic chemistry. There are some organic compounds that they don't do so in what?
Simple number ratio.
That is, they carry numbers that are different. They don't do so in simple number ratio. And another one. What's the last one?
For any
there's always combination or separation of atoms. Yes or no? That one there's no modification. That one is true. That one is true. No modification. It's not possible for you to add any combination without combination or separation of atoms. Without what? Now, I didn't move from that place. I didn't enter from the electric emission. Yes or no?
Yes.
I told you that if we discovered that wave can behave as two things. Wave can behave like light can behave as two things.
Yes.
And I say particle of light is called what? Photon. Particle of light is called what? Photons. Yes. And I say when we now want to use light to eject electrons away from metal surface, that's what we call photoelectric. That's what we call photoelectric. I say you first have the light to have an energy, which is HF. Have you know? The one that we use to carry the electron, so the object dinner, is one called yes or no? The one you now want to use to run away with it is one called yes or no? And we saw question on that part. Have you know? Now move to radioactivity. I said we have 3 particles. We have alpha. Okay, which one is that? When they put lead block in his front, it will not have effect. Because it does not have mass.
Yes.
People like that. They only deflect it. So I told you guys that it's okay you're going to deflect it. But story you only mass can deflect. So it's better that we deflect most. Yes or no?
Yes.
Yes or no?
Yes.
So at the end of the day, I still can say one have penetrating power than the other. Which one have highest penetrating power? Why do you have highest penetrating power? Which one have less penetrating power? Yes or no? Because and we say alpha is what? Is nucleus of helium. Yes or no?
Yes.
Atom of helium. Helium is 4-2. Yes or no?
Yes.
Beta is what? Beta is and gamma is what? Yes or no?
Yes.
So at the end of the day, and I say when you are adding and subtracting, when you want to add, that is when we have fission or fusion. I say one is fusion, one is fission. What do I call fuse? I say fuse is what? When it's together, what's now fission? Separation. That is olayo kan over to méjì. That's fission. One méjì over so there, but that's what? That's nuclear fission and nuclear fission. Under nuclear fission and nuclear fission, the thing that was happening at your left was because the thing that you have. That the summation of mass number at your left is equal to summation of mass number at your right. And summation of atomic number at your left is equal to summation of atomic number at your right. Yes or no?
Yes.
Yes or no?
Yes.
Yes. And I talk about something that we call half-life. I say half-life is the time that is taken for you to divide into half. Yes or no?
Yes.
That is the time you have to cancel imaging and in half-life. The time we call into two is the one called what?
Half-life.
I gave you one formula for half-life. I say half-life is equal to ln 2. That's 0.693. All over what? Decay constant. I say lambda is decay constant.
Yes.
So I say half-life is equal to 0.693 over what? Decay constant. Yes or no?
Yes.
Yes or no?
Yes.
And I say that decay constant at the end of the day, decay constant is now 0.693 over half-life because one was multiplied. Yes or no?
Yes.
And I gave you one formula. I say number remaining. Number remaining is equal to what? What is n? N is equal to what? C over E. Abi now? Is equal to T all over T half. Yes or no? And then there's something that we call Ojeradano. And there's something that we call Oku. Yes or no? When they say disintegrate away, we will say when we get the fraction of the one that remains, we will not say 1 minus fraction that remains. Abi now? Is the one that decay away. Yes or no? That is, I was saying out of means division. Out of means what? Division. So if I say 1 all over 12, or if I say 1 all over 16, that is 1 all over 16 that remains. So make the lower J than by 16. Yes or no? So the fraction that decay away is what? 15 over 16. Yes or no?
Yes.
Did I say more than that in this class?
No.
That's all about modern physics. That's everything about modern physics. So you should try your modern physics.